Hi. In this second and last presentation addressing thread-level parallelism, we will look deeper into the two classes of shared memory multiprocessors that were referred in the previous presentation. After watching this presentation and completing the learning task proposed at the end, you should be able to explain in further detail the operation of the centralized shared memory and the distributed shared memory multiprocessor systems, and also to describe the two classes of cache coherence protocols referred here, snooping and directory-based. Symmetric shared memory machines usually support the caching of data that are used by multiple processors. That's shared data, and also of data that are used by a single processor, and that's private data. And this is an important communication mechanism among the various processors through reads and writes of the shared memory. But at the same time, it raises a problem, which is how to ensure cache coherency. The coherence problem exists because there is a global state defined by the main memory, and then there's a local state that is defined by the caches that are private to each processor. Informally speaking, we can say that a memory system is coherent if any read of a data item returns the most recently written value of that data item. Let's look at this example. Initially, neither cache contains the variable x, and x has the value of 1. Then the two processors read x in sequence, followed by a write operation by a that changes the value of x to 0. The situation shown in the last line of this table is what we must prevent, since the cache of b is now out of date, and so b will get a wrong value for x if it reads it from its local cache. Migration means that a data item can be moved to a local cache and use it there in a transparent manner. Coherent caches also provide replication for shared data that are being read simultaneously. Instead of trying to solve the problem at software level, multiprocessors use a hardware protocol to ensure cache coherency. There are two classes of these so-called cache coherence protocols called directory-based and snooping. The first class is called directory-based because the sharing status of a particular block of physical memory is kept in one location, called the directory. And notice that in centralized shared memory systems, which we are now considering, we can use one centralized directory. This solution is not appropriate in the case of distributed shared memory systems, where a single directory would be a point of contention. We will see later how the directory-based solution can be adapted to cope with the distributed shared memory architecture. The second class is called snooping, and in that case, every cache that has a copy of the data from a block of physical memory could track the sharing status of the block. Let's look at a specific example of snooping for centralized shared memory systems. This slide shows one method that belongs to the snooping protocol class, called the write-invalidate protocol. Briefly speaking, this method ensures that a processor has exclusive access to a data item before writing that item. What this means is that no other readable or writable copies of an item exist when the write occurs. All other cached copies of the item are invalidated. This is what happens when processor A writes 1 to variable x in this example. As we saw in the previous example, a snooping protocol requires communication with all caches on every cache miss. This is not feasible in the case of distributed shared memory systems, where the increase in memory bandwidth and interconnection bandwidth comes from distributing the memory. So unless we eliminate the need for a coherence protocol, for the coherence protocol to broadcast on every cache miss, distributing the memory will bring little advantage. In this case, the directory-based coherence protocol is preferable. Let's look at an example. You may recall a similar diagram that was shown in the previous presentation, the main difference being that we now have a directory added to each node to implement cache coherence. Each node is shown as a single multi-core chip, and the directory information for the associated memory may reside either on or off the multi-core. The coherence mechanism will handle both the maintenance of the directory information and any coherence actions needed within the multi-core node. Well, just as in the case of a snooping protocol, there are two primary operations that must be implemented by a directory protocol: to handle a read miss and to handle a write to shared clean cached block. To do so, directory-based cache coherence protocols define 3 states for every cache block, as indicated in this slide. Shared, where one or more nodes have the block cached and the value in memory is up to date, as well as in all caches. Second one is uncached, where no node has a copy of the cache block. And finally, the third one, modified, where exactly one node has a copy of the cache block and it has written to the block, so the memory copy is out of date. And in this case, the processor is called the owner of the block. Well, as a final learning task in this subject, I would like to invite you to read the 2 sections of the book that present examples of snooping and directory-based cache coherence protocols. Please read through the pages indicated in this slide and make sure that you understand the operation of these 2 cache coherence protocols. And that's it. Thanks very much for your attention.